All right, welcome ladies and gentlemen. This is video number 4 in our gases unit. This video is going to be on the ideal gas equation, what it is, and then how we can use that to answer questions about relative amounts of gas. So first up, ideal gas law. So we've talked about ideal gases, this idea of gases being perfect. We know that they aren't actually perfect in real life. It's the difference between ideal and real. However, real gases tend to be close enough to ideal gases that we treat them as ideal unless the problem sort of tells us not to. And if we treat gases as being perfect, even though I know we're not, it actually allows us to do an additional calculation using something called the ideal gas law. And what the ideal gas law, because remember gas law is kind of like a formula, it actually allows us to bring moles into the equation to actually calculate moles of gas under certain conditions. So this right here, PV equals nRT, this is the ideal gas law. And this is like a really big, really famous almost equation in chemistry. It's used a lot. There are components of this that you already know, right? PV and T, pressure, volume, and temperature, which means that there are a couple new things, N and R. So R is a gas, is what is called the gas constant, which means that it never changes. It means that you're never going to get R given to you in a problem because you know it's always going to be this particular number, 0.0821, and then it has these units of liter atmospheres per mole Kelvin. It's a sort of crazy mishmash of units. They're basically combining a whole bunch of units, volume, pressure, moles, and Kelvin. Moles is actually N in this equation, lowercase n. And the reason that it's lowercase n, sort of we talked about the reason why it's not M. We have so many M's in chemistry, mass, molecular weight, molarity, molality, that they had to go to the next letter in the alphabet to have the one letter abbreviation. So N is actually moles. And then P is pressure, V is volume, and T is temperature. Key thing though is that we need our units to match with the units for R. So whenever we're doing pressure with PV equals nRT, if we're using the 0.0821, the pressure has to be in atmospheres, the volume has to be in liters in order to match, and this shouldn't come as a big surprise, but the temperature has to be the temperature in Kelvin, again, because we can't have negative values for pressure, volume, or moles. You can't have negative moles of something. So we need to use the absolute temperature scale, a temperature scale that can't be negative. So PV equals nRT is really just a fairly straightforward chemical equation, I should say, formula, and we can use it to calculate for stuff. So we have an example here. A sample contains 2.24 liters. Oh, okay, there's a volume of methane gas at a pressure of 1.48 atmospheres. Okay, there's a P, and a temperature of 315 Kelvin. There's a T. How many moles of CH4 does the sample contain? So it gives us pressure. It gives us volume. It gives us temperature. And it asks for moles, so that's N. And we have PV equals nRT, which means the other thing that the problem hasn't given us is R. But remember, R is a constant. R is never going to change. It's always going to be 0.0821 liter atmospheres per mole Kelvin, which means that we have P, we have V, we have T, we have R, and we're solving for N. So we have everything that we need, and then we're just plugging in and solving. So that's all you got to do with PV equals nRT. So just plugging everything in, 1.48 atmospheres times 2.24 liters equals N times 0.0821 liter atmospheres per mole Kelvin times 315 Kelvin. Multiplying the stuff together on the same side, I get 3.3152 equals N times 25.8615. So at this point, if I want to solve for N, I'm going to have to divide by the thing that N is being multiplied by. So divide both sides by the 25.8615. That'll go away, and then I do the stuff on the left, and I get N is equal to 0.12811905, and it sort of keeps going. And how many significant figures should my answer have? Well, looking up the problem, there are 3 sig figs in the pressure, 3 sig figs in the volume, 3 sig figs in the temperature, which means I'm definitely going to have 3 sig figs in my answer. The 0 here doesn't count, remember, sort of coming in from the left side, but I want to keep the 1, the 2, and the 8, and then cut it off. In terms of rounding, I'm not going to round up, so my final answer, 0.12811905, 0.128 moles. And that's PV equals nRT. Now, the thing is, we have two formulas, right? We have the combined gas law now, P1 V1 over T1 equals P2 V2 over T2, and now we have the ideal gas law, PV equals nRT. When to use which one? Because the problem isn't necessarily going to tell you, hey, you need to use PV equals nRT here. So notice that in the combined gas law, two sets of conditions. This is how you're going to know that, that you're supposed to use the combined gas law. Two sets of conditions. They're going to talk about a before and after. You are changing the system in some way. You start at some set and then they do something, they change it, and then you get a new set of conditions. You do not have that in the ideal gas law. Also, you probably won't be given moles in the problem. In the ideal gas law, there's no moles in that equation. Sorry, for the combined gas law. The ideal gas law, we're going to use PV equals nRT if you only have one set of conditions, one pressure, one volume, one temperature, versus, you know, up here, we're going to have two pressures, two volumes, right? Two sets of conditions, two temps. Or moles, right? That difference that we have n right there. If the problem gives you a mole number or it asks you to calculate moles, then hey, we're going to be using PV equals nRT. So we want to kind of look for code words in the question to figure out when to use which. Amounts of gas. Now with PV equals nRT, if we think about it, if pressure, volume, and temperature is the same for two gases, you have two different gases, but their P, their V, and their T are all the same, then the number of moles of gas must also be the same, right? This thing right here, if PV and T are all equal, then when you plug it into the combined gas law, because R is a constant, you will get the same number of moles. Moles is how we talk about amount in chemistry, right? 1 mole is always going to be the same amount as 1 mole, even if they're two different substances. It's the same amount. So for us, the big key point is right here. If you have gas samples that have the same volume, the same temperature, and the same pressure, then we know that we have the same amount of gas in each one. And it's important to recognize that it's the same number of gas molecules, not the same number of gas atoms, same number of gas molecules, but same conditions equals same amount. And there are a number of multiple choice questions that deal with that. So just as an example, very typical Regents question, which gas sample at STP has the same number of molecules as a 2.0 liter sample of Cl2 gas at STP? First up, in this problem, it does not matter at all that it's chlorine gas, nor does it matter what the gas is in each of these cases. That's not what you want to look at. That doesn't have any effect at all. What we want to pay attention to, which gas sample at STP has the same number of molecules of the Cl2 also at STP. Notice, same conditions, same temperature, same pressure. So if we want to find the sample that has the same amount as this gas sample that has a volume of 2 liters, what we need to do is find the choice that also has 2 liters. Same conditions. If gas particles are under identical conditions, it doesn't matter what the gas is, you know you will have the same number of molecules as that other sample. So again, the identity of the gas doesn't matter. What matters is you're looking for the thing that is under the exact same identical conditions. So that is the ideal gas law, and that last question is definitely an application of the ideal gas law. And as always, we will be practicing with this in class.